Hello everyone, I am BHAVAGNA, currently in BTech first year pursuing data science and artificial intelligence at IIT Roorkee. In this video, we will try to solve the problem statement of identifying prime numbers and their arithmetic progressions in a given range, emphasizing on the fact that we are going to employ the Sieve-Eratosthenes for effective prime number generation. Before jumping into the actual code, let us go through the basic definitions as to what is a prime number and what is an arithmetic progression, just in case anybody needs clarification. Moving to the next slide, uh, introduction to prime numbers. What is a prime number? A prime number is a natural number greater than 1 that has no positive divisors other than 1 and itself. So basically, the factors of a prime number are just 1 and itself. Examples being 2, 3, 19, 97, etc. And we will be using the algorithm, the sieve of Eratosthenes, for efficiently finding all the prime numbers up to a specified limit. And what is an arithmetic progression? An arithmetic progression is a sequence of numbers in which the difference between any two consecutive terms is constant. And this constant difference is called as the common difference. A classic example being the first five even numbers, even natural numbers, 2, 4, 6, 8, and 10, common difference among them being 2. Um, so let us discuss the goal of writing this code. The ultimate goal of this code is to find and show groups of three prime numbers that form an arithmetic progression within a specified range, this range being the input given by the user themselves. So the code that we are going to write will list down the prime numbers which form an arithmetic progression in groups of three until a specific range or limit is reached. Moving to the next slide. So how are we going to write this code? So by now you would have recognized the need to identify and group prime numbers and list them down separately so that we can look into the patterns that they fall into. So first let us list down the objectives that we wish to complete by writing this code. The first one being prompting the user to enter an upper limit for the range of the numbers and then applying the Eratosthenes and then creating an empty list and adding all the numbers that are still listed as prime into that list. And next one being identifying the arithmetic progressions among those numbers. And the last goal being printing out all those numbers so that the user can read it or use them. Moving to the pseudocode, the first part of the pseudocode. So what you see here is basically the pseudocode for the function of sieve of Eratosthenes, this part, and this is to create a list to store all the prime numbers for which we will be employing a specific data structure called as vector. You can pause the video here to take a better look. I will be moving to the next slide. So this particular piece of code is the code for vector. This particular line of code uses a vector data structure, as you can see. So what is a vector? In C++, a vector is a dynamic array that can grow and shrink in size as needed. Unlike the regular arrays, vectors can automatically adjust their size when you add or remove elements, which you will realize is important as we further move in writing the code. Vectors are part of the standard template library in C++, so you need to include another specific library in order to use this data structure. If you look at the syntax of this specific line of code, what you see here is vector int. This is the data type that the vector is supposed to store or expected to store, and this primes is the name of the vector that we are generating, and this particular line of code will command the sieve of Eratosthenes function, which we will be defining in the next few minutes of this video. Moving on. Coming to the major part of the video, that is the sieve of Eratosthenes. Before writing the actual code for the algorithm of sieve of Eratosthenes, let us first understand how it works. Using an example, say you want to list down all the prime numbers from 2 to 100. How do you do it using this particular algorithm? First, we start down by listing all the numbers from 2 to 100. Then Starting from the first prime number, which is 2, we mark all of its multiples like 4, 6, 8 as being not prime. Then we move to the next number, which is still marked as prime after the whole process that has been followed above. And then we repeat the process again and again. We continue until we have gone through all the numbers up to the square root of our range, which is given by the user. One must understand that we only have to check the numbers up to the square root of the range, because any non-prime number larger than that will have a factor less than or equal to the square root. So that number would have already been cancelled, so we don't have to employ other numbers in order to cancel uh, the numbers that are greater than the square root of our particular range. We can also speed up this process by cancelling out the multiples of the numbers, those which are still marked as prime, greater than or equal to the square in the second step. We can skip this step or we can use this particular step because it can improve the time that is being taken for the whole program to work, which can speed up our process, which will become a crucial part when we discuss about the efficiency of the code that is being written. Uh, so let us together try to identify the primes from 2 to 100 using the CWF Eratosthenes. Uh, Starting from the first step, listing all the numbers down, which we have done. And the second step is to cancel or mark all the numbers which are multiples of 2 other than 2 from 2 to 100 as being non-prime, um, which are 4, 6, 8, 10, and basically all the even numbers. Can cancel this part. If you can see, 3 is still marked as a prime number, so let us repeat the step 2 for 3. That is 9, 15, 21, 27, 33, 39, 45, 51, 57, 63, 69, 75, 81, 87, 93, and 99. And the next number being 5. So let us look at the numbers greater than or equal to the square of 5, which is 25. As you can see, the multiples of 5 which are less than 25 have already been cancelled out. So in order to speed up the process, we can start marking from 25. So 25, 35, 55, 65, 85, and 95 are not primes. And next 7, repeating the same process. 49 and 77, 91 and 8, 9, 10 have already been considered as not primes, and we don't have to check after 10 as we have discussed before. So let us mark all the numbers which have not been cancelled out as being primes. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 47, 43, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. So the number of primes 4, 4, and 2, that is 10, 10, 12, 15, 15 plus 2, 17, 17 to 19, 19 plus 6, 25, 20, all the 25 primes from 2 to 100. So this is how we find out the primes from 2 to 100. Using the same logic, let us try to write the code for the sieve of Eratosthenes. So let us try to understand the code for the sieve of Eratosthenes. As you can see, this particular piece of code is basically the function to implement the sieve of Eratosthenes. We will be defining this particular piece of code, this function, before the main function, that is the int main. And let us try to understand the syntax that is being used here. If you observe the first line of the code, that is us defining the function named the sieve of Eratosthenes, which is basically a function of int range, that is an input from the user themselves. And the vector int here is basically the return type of the function when it is run successfully. That is, we will be returning a list of integers if the function runs successfully. Coming to the next line of the code, that is vector bool is prime. This basically creates a list called is prime where each number from 0 to range is assumed to be prime initially. So it is basically a list of all true. That is, you can assume it to be looking like this. So it is basically a true, true, true. So as we move through further lines of code in this particular function, we will be testing the genuinity of this particular truth. So the final code will be something like true and false, false, true, where we will finally be omitting out all the numbers that have been found false to give us an output of the numbers containing the list containing all primes. So let us see how this is done. Going through the next lines of code, you can see that we defined is prime 0, is prime 1 is equal to false. That is, we are manually marking 0 and 1 as false because they are not prime numbers. And to the next piece of code, which is for loop. This basically starts at 2, which is the first prime number, and continues up to the square root of the range. Why square root? We have already discussed this point because any non-prime number must have at least one factor less than or equal to its square root. So employing this particular function until its square root is enough if we want to improve its efficiency. You can also employ it until range itself, but it will be more efficient if we do it this way. And the next piece of code, the next line of code, which is if is prime I, this is an internal loop. This will run if the current number I is still marked as prime. So we will move forward if the current number I is still marked as prime. So let us assume the current number after running all this code is still marked as prime. So the next loop is a for loop, which basically marks all multiples of I as being non-prime, which is logical, as any number that is a multiple of another number which is not 1 and itself is not a prime. So this particular piece of code will make sure that all the multiples of uh, a number that is so been qualified as prime will be considered or cancelled out as non-prime. What we have done in the previous slide in step 2 is being done here. And the next piece of code will collect all the prime numbers and make a list out of it. So this particular piece of code will form a list of form a list which is a vector to store all the prime numbers which we have found. This basically checks all the numbers from 2 to range, and if the condition is satisfied, the loop will make sure the I is included in the list that is being returned. And if you can see here that there is a particular line of interest which is primes pushback. So this is a method used to add elements to the end of a vector. For example, if I is a prime number, we will if I is a prime number, we will add it to the vector called primes using this particular piece of code. So in this code, after determining which numbers are prime by checking the Boolean vector, the function adds those numbers to the prime vector. That is, say a number I qualifies through all these steps and has finally reached to this point. So this will be included in this particular vector to be returned. So this whole return prime will contain this particular I. Moving to the next slide. So this is basically the second part of this flow code, which we will be using for finding the arithmetic progressions among the prime numbers that are listed. You can pause the video and take a look at it. I will move on to the next slide. So let us try to understand the code for arithmetic progression. This particular piece of code is expected to print out the arithmetic progressions among prime numbers. Uh, if you see, this is basically a combination of loops. If you try to understand the outermost loop, that is this for loop, it basically has a purpose to iterate over each prime number in the vector primes, which was previously populated using the sieve of Eratosthenes, if you remember. And if you try to understand the syntax that has been used here, this size t is an unsigned data type used for indexing and presenting sizes, especially uh, when this particular value is expected to be non-negative. And this particular piece, prime size, basically indicates the size of the vector primes that has been returned before. And what this does, let's say, chooses a particular first term in the set of primes that has been returned. Let us say it chooses 3 for now. That is, the first term that we are defining further in the code is 3. Let us assume. And if we move on to the second part of the code, that is the inner loop, the second loop is for selecting the second term basically. So what it does is that it picks a second prime number from the primes vector starting from the prime immediately after the first prime. We make sure that this condition is included while we are coding because we don't want any repetitive or redundant sequences, because 333 would also form an AP, but it would be useless stating it. It would be practically useless stating it. So what it does is it checks for the second term from the terms after 3, and it does not check before 3 because we don't want any redundant sequences as we have stated before. So as you can see, the first term and second have been given have been stated as variables under the integer data type, and we have also defined another variable called difference under an integer data type, which is defined as the second term minus first term. What we are basically trying to do is to extract the common difference. We are basically choosing a first term and then randomly choosing a second term. Randomly in the sense choosing a number after our first term in an order way. That is, we check for the first term, we check for values of the first term. Say this is the nth term, and then we choose the n plus 1th term, and then later we check for n plus 2 and so on until the limit is reached. So let us understand what it is, and then we choose a second term out of these in an orderly way. And what it does is it finds a common difference d, a difference d, and we define a term, third variable, which is uh, under the name third term, which is an integer data type, which will be defined as the second term plus difference. That is, let us say I have chosen 5, which is the prime number that is following 3 immediately in the vector primes that has been returned. So what it does is it calculates d, which is 2. So now I defined the third term, which is second term plus difference, which is supposedly 7. Now what the next part of code does is that it checks whether this third term is in the defined vector primes or not. If it is, the next piece of code runs and it will be returning the first term, second term, and third term with spaces, as you can see here. And what happens next is that the code stops running. That is achieved using this particular piece of code called break. What it does is that uh, it returns out of the loop. It comes out of the loop after a particular three-membered arithmetic progression is found. Then the whole thing is executed again. Uh, it executes until all the numbers are covered, all the prime numbers are covered, and all possible sequences have been achieved. Let us assume that I have chosen something like 17 and not 3. Like after running 3, 5, and 7, finally my code has come to somewhere over 17. What it does is it checks for the next term, this second portion, checks the next term, which is 19. So what is the common difference here? It is 2. So what is my next term supposed to be? 21. But we know that 21 is not a prime and it is not included. So this will not be further processed in this particular area because this is not satisfied, and this thing will run again, uh, neglecting 19 here. It uses 17 as the first term again, and it will choose the next prime number, which is going to be 23, and it will try to check again, and it iterates over and over until our final goal is reached. That's how it works. I hope you can comprehend what is happening. Moving to the next slide. Um, Let us try to test the code that we have written so far. As you can see, I've included libraries that are IOStream and vector. And using namespace std was included in the code for us to remove writing std every time we write cout or cin for the benefit of the coder. And we'll see the code and then we'll try to test it. You can take a look at the code that is being written. So let us assume the input being given is 10. So we can see the output is 357, which means 357 are the primes which are in AB under the given particular range. Other inputs like 20, 100, and 500 were also given to test the code. These are all the primes that are in AP from 2 to 100. We have used a bigger number in order to like expand the range of the code that has been written. And you can pick any particular line among all these and you can check whether it satisfies the condition of AP or not. I have included the screenshots of the outputs that we have received. As you can see, so let us pick a random line that is 11, 29 and 47. As you can see, the difference between 11 and 29 is 18, and so is the difference between 29 and 47. So these numbers are in AP and are being listed in the given code. Moving on. I have also listed down the libraries, functions, and statements, and also the data types that have been used in this particular code. You can pause the video and go through all of it if it's necessary. And that's it. That is how you write the code to finding the prime numbers and the arithmetic progressions in a particular range. Thank you.